So you can still see the screen, eh? Hello?
Yes, can see.
Okay,
Hello.
good. So I will get started. So today, last time I think we stopped around here, I think. I will send you the link to the book that you will be using in a minute, maybe after we are done with the class. So today we shall talk about functions and homeomorphisms. Again, this is not entirely new to you. So it's more of a revision of what you did in SMA 101. And maybe you'll encounter it again in set theory when you're, if you haven't done it already. Have you done SMA 202?
Yes.
You're doing it now, or you have done it?
We are doing, we are doing it now.
Yeah, I think you'll encounter functions again there. Is someone trying to join? Let me admit them, then we can continue. So today we shall start on this section for functions, talking about functions and homeomorphism. So we'll define a function. A function is usually requires two things. You need a domain and a codomain. So the domain is X in our case, and the codomain is Y. And then you need a rule that picks an element from X and assigns it to a unique element of Y. So that gives you a function. So the keyword here is unique. So if I have an element from X, it can only be assigned to a unique value in Y. So for instance, if I have 2 being assigned to 3, I cannot have the same 2 being assigned to any other value. It must be assigned only to 3. It's possible for me to have another element in the domain which will still be assigned to 3. That is okay. The only thing that cannot happen is that I cannot have a number being assigned from X being assigned to 2 numbers or more than 2 numbers in Y. So that's a function. So I think you are familiar with these injective and surjective functions, and a function will be bijective if it is both injective and surjective. And once you have a bijection, we can always find the inverse of the function. So you've learned about the inverse. I think you must have done it in SMA 101, basic mathematics, and you must have done it. You will do it again, I think, a bit of it in set theory. Or so I hope. So as a small exercise before we proceed, maybe you can try to do number 1 and 2. There's a small exercise here for you. Try to do number 1 and 2. Or maybe number 1 and 3. Do number 1 and 3. And give me your results. So I'll give you about 5 minutes to do that. The rest you can do later. So I want you to read this question and do number 1 and number 3. So Paul, now you can pull out your kitabu and kalamu. So you need to do number 1 and number 3. If you are done earlier, you can let me know. and give me your explanation for your answer. So wangapi wamemaliza? Or you are waiting patiently until I say we can now move on? You have a strategy. So Rani amemaliza?
Yeah, I'm done.
So what do you have for number one?
Number one cannot be a choice because
Yes.
the range has to include non-negative and negative real numbers. So I think that because of the negative one that is included in Y, that disqualifies it.
So basically what you have is you need to be able to map points from the set X to the set Y. So if I pick points from the set X, is it possible to map, to find an image for them in Y? Can I find the image of all the points in X? You have gone quiet. So for X, it makes sense because any point I pick in the set X, I can find something in Y where it will be mapped, right? Because if you square any number, you'll always get a positive number. So all the numbers, and the smallest one you need is 1, which is already included in y, because 1 squared is equal to 1. So you'll be just fine with x and y. So the only thing that will happen is it will not be a surjective map. It will not be onto, because there'll be some numbers in the range that is from -1 up to 1, but not including 1. All those numbers will not be covered. So it will not be onto. There's some numbers in the codomain that will be left out. So the range here in particular will be from 1 to infinity, and it's already included in y. So it makes sense. The only thing that will happen is that the map will not be onto. So is it an injective map? You've gone quiet again. Okay, how about number 3? Anyone with the solution for number 3? A good idea is to try to sketch the graph in the interval -2, 0 and see what happens. Leo mmeamua kunyamaza kabisa bana. It looks like you know that I am time limited, so if you wait long enough I will eventually leave. Paul, what is happening to the class bana? They are not active. Hey, okay. Let's we'll continue then.
I think I've found for 2.
Okay, you have decided to do number 2. So tell me what you have done for number 2.
I found that for number 2, some of the elements in the domain will not be mapped onto the code domain.
Yeah, that's correct. So that one doesn't make sense.
Yeah.
And number 3?
I think for number 3, all of them, all of the elements inside the domain will be mapped, so it makes sense.
Makes sense. Is it a bijective function? Is it a bijection? Another question, is it 1-to-1 and onto? The best thing is to draw the graph in that interval from -2 to 0. Now, in that interval, you can check whether it's 1-to-1 by drawing a horizontal line. If the horizontal line cuts the graph only once, then the graph is 1-to-1. If the horizontal line cuts the graph more than once, then it is not 1-to-1. So, but you must work only within that interval from -2 to 0, not outside the interval. So what do you have? So x definitely makes sense. Pardon?
I think it is 1-to-1.
Yes, and
because all of them, like the horizontal line can cuts across it once.
only once, yes. What about, is it onto? Are all the elements of y taken up by this function?
Uh,
Are you the only one answering bwana? Si watu wakusaidie ama itabidi wakulipe sasa?
I think
So
all of them. I think all
you
of
think-
them are being taken up because
You think, or you are sure?
not 100% sure.
Okay, all of them will be used up, and you can see it straight from your graph.
Yes, all of them.
You should be able to see that from your graph. But secondly, you can prove this algebraically as well, but we will not do that now. So continue with the rest of the exercise in your own time. For now, we'll move on to the next slide. So we now look at another into the same function, and we check how it behaves when we restrict the domains and the codomain. So the function we'll consider is f of x is equal to x squared, and we take x and y to be, in the first instance, we take x and y to be the set of real numbers. So that's the whole of the number line from minus infinity to infinity. So in this case, again, we see that f is surjective because not the whole of y is taken up. All the negative numbers of y will not be taken up by this map. So this map will not be surjective under these conditions. It will also not be injective because we can have two different numbers being mapped onto the same thing. So it is not injective. So and in this case we can't find the inverse, because for us to find the inverse, the map has to be a bijection. It has to be 1-to-1 and it has to be onto. But if we make some adjustments and we limit the domain, just run from 0 to infinity, and also limit the codomain to run from the same 0 to infinity. So everything will just lie within the first quadrant, this one here. So if we restrict ourselves to that point, then we can see that the map is definitely injective, because if you draw, it's injective and surjective as well, because as you keep getting larger and larger values of x, you'll end up using up the whole of the y-axis, and therefore it is surjective. And if you draw a horizontal line, that is, if you restrict yourself to just this first quadrant and you draw a horizontal line, it will cut the graph exactly once, and therefore the map is injective. And if it's injective, now we can compute the inverse. The inverse will just be this red line, the part that is above the x-axis. That is the inverse that we shall, just the red line only. Okay, so that's an example of a function, and we have shown that by limiting it behaves differently if you use different domains, and you can limit it in such a way that you are able to get an inverse within that limited domain. So now we talk about continuity. The continuity here will appear a little different than what you have seen in calculus. The definition will be a little different, but it's still equivalent. It can be shown that this definition is equivalent to the one you have learned in calculus. I think you may meet this as a theorem in real analysis, introduction to real analysis. So let's define this. Let x and y be the sets of points, and let f be a function from x to y. So we say that f is continuous whenever a sequence of points in x converges to a point x in x, then the corresponding sequence of points determined by evaluating the function at the points in the sequence xn will also converge to the value of the function f at the point x. So we usually, convergence requires to measure some closeness, and that is measured using the Euclidean distance, same distance that you are familiar with for points in space. So this defines a continuous function. So that means if you're given a function and you want to show that it's continuous, you have to find a convergent sequence in x, which converges to a point x, or rather you show that if a sequence converges, any sequence rather converges to a point x in x, then the corresponding sequence obtained by evaluating the function at each point in the original sequence will also converge, and it converges to the value of the function at the point x. So we shall use this in the next example, so keep them in mind. So here is another example. We have two sets. One is a subset of the real number line. The other one is a subset of a two-dimensional space, R2. So it's made up of ordered pairs. So we define a function from x to y as follows, where any element we pick from x, we say small x, is mapped onto x squared, the ordered pair x squared. Now, clearly, G is a bijection because you can, we check first that it is injective. So it's injective because if x1 is not equal to x2, then you can clearly check that f of x1 will not be equal to f of x2. This is possible because we have limited ourselves to positive numbers. If you had negatives at all, maybe that would not have worked. Positive numbers in the domain. Now, again, you can check that it is surjective because if you pick any element xy in the core domain, then y must be equal to x squared, and it will, and if you pick, it will be possible to find an element in x such that f of x is equal to xy. This will always be possible, and that says the map is surjective. So since the map is both surjective and injective, we can conclude that it is a bijective. Now we can also check if it is continuous. So we pick a sequence of points in x that has a limit x. In other words, it converges to small x. So that means using the properties you will learn from real analysis, if xn converges to x, then xn squared must converge to x squared. Hey, we have a resident DJ. Okay, he has put off the music. So hey, what is going on? So so we can get the value if we need to show that G is a continuous function. Now, what is going on here? I've mixed up the letters. I think I've changed this to G when it should be F. Or the ones that are up here should be G, so that we are consistent through. We need one letter to represent the functions throughout. So we'll just continue with G. I think I will change everything else to G before I share the slides. So assuming we use G as the function, then we evaluate the function at any point in the sequence, xn, then we'll get the ordered pair xn squared. But since xn converges to x and xn squared converges to x squared, this ordered pair will also converge to x, the other ordered pair, which is x squared. And this is precisely the value of the function at the point x. This means that the function is continuous, according to our definition. And since the function is bijective, it must have an inverse, and that inverse the inverse basically takes us back from y back to x. So if you pick an ordered pair in y, the corresponding element that is mapped onto that ordered pair will be x in the capital X. So this map is called the first coordinate projection because it simply picks an ordered pair and maps it onto the first coordinate in the ordered pair. So it's called the first coordinate projection function, and it is continuous again, as you can see in what follows. Because we pick to check now that's so continuous, because G inverse will have its domain as y and the codomain as capital X. So it means you have to pick a sequence here in y which converges to x. Now it converges to this xy, but we know that G inverse of any element in the sequence will just be equal to xn. This should not be an equal sign, it should be an arrow. Xn converges to x, so it should be an arrow pointing towards x to show that this xn converges to x. That is already stated in the theorems in the example, so or assumed to be true in the example, so you can use it. But we know that x is precisely the value of the function at the point xy, and therefore the inverse is also continuous. So here we have a function which is bijective and it's continuous, and the inverse also turns out to be continuous. So this function is illustrated in this diagram. The points of y will be the graph. The graph of y is equal to x squared. So those ordered pairs that lie on this curve will be the elements in the set y, but we'll have to limit the values of x from 0 up to 4, right? So then the 0 up to 3. Then the set x itself will just be points on the number line from 0 up to 3 inclusive. So you can map from the segment from 0 to 3 onto the points along the curve by just stretching a vertical line all the way up. Then you will be able to find the mapping. So this is not quite the graph of well, it's a graph of G, but it also illustrates the point. So what we have done is we are doing two things. We are selecting the set y to be the set of points on this curve between 0 and 3, and then we are taking the capital X to be the set of points between 0 and 3 along the x-axis, and we map the points on the curve to points on the x-axis using the straight lines. So this gives you a bijective function whose inverse is also continuous. So now let's define homeomorphic sets. So if x and y are two sets of points in space, then we can say that x and y are homeomorphic if there exists a continuous bijection from x to y whose inverse is also continuous. Exactly the example we have shown above in the previous slide. If such a mapping exists, such a bijection exists, then we call it a homeomorphism, and we say that the two sets are homeomorphic. And when this happens, if you have two objects that are homeomorphic, we can say that they are topologically equivalent. So we look at an example. The half-open interval, for example, is not homeomorphic to the unit circle because you can try to do this through some graphical techniques, which is what happens at the bottom. You try to bend the half-open interval into a circle, but it can't become a circle because there's one side which is not included. See this point, it's closed on one side but open on the other end, so you cannot, it's not possible to join them, form a circle. The other way to look at it is to use cut points. If you have the unit circle, if I cut it through one point, I don't split it into two, but if I cut the half interval, or the half open interval at one point between 0 and infinity, it is automatically split into two pieces. So that is one property that should be preserved if two objects are homeomorphic. If I cut one and it splits into two, the other one should behave the same way if they are homeomorphic. So in this case, they don't behave the same way, and therefore the two will not be homeomorphic. So we can also construct a homeomorphism from a sphere to the surface of a cube in the following steps. So we first of all take a sphere and put it inside the cube, so it's wholly sitting inside the cube, and pick P0 to be a point inside the cube, but it shouldn't be on the surface. No, a point inside the sphere, not in the cube. It's inside the sphere, but should not be on the surface of the sphere. So we pick any point P on the sphere and draw a ray from the point P0 that is inside the sphere. The ray starts from P0 and goes all the way through P and right through to the cube, surface of the cube. So you can see here the point P0 is inside the sphere. If I draw a straight line from there through P, it will pick a point P on the sphere and map it to a point P on the cube. So through such a function, we are able to pick any point on the sphere and map it to some unique point on the cube. Now, this function is definitely a homeomorphism, but this is just by construction. So we can't use the formal techniques that we've been using to check that's a homomorphism. So earlier on, we learned about isotopic objects, and today we have also learned about homeomorphic objects. Now, two objects are said to be isotopic if one can be transformed into the other by using a finite set of continuous transformations. So it depends on the space in which it is. In some spaces, two objects will be isotopic in other spaces, they will not be. But if they're isotopic, they are automatically homeomorphic. But being homeomorphic does not necessarily mean that the two objects are isotopic. So we will stop there for now, and we'll continue next time so that you have time to go to. I've also run out of slides, but this will give you time to catch up with the next class and also complete this exercise. There's this exercise that you need to complete. So this is for your own practice. So I'll be sharing the soft copy of the book that I'm using for this course to Paul, and then we meet again next week. So the book has more detail. You can try to read the book and capture more detail as we go along. I will also send a set of questions for you, tutorial, which can help you grasp the concepts better. So if there are no questions, we can end the class now.